Greetings peeps, this is your introduction to 2D projectile motion. Oof, okay. There are three types, very quickly, I'll name them. There's the cliff style projectile motion, hafabola trajectory. Number 2, there's a launch at an angle, symmetrical philabola trajectory. And number 3, launch at an angle, non-symmetrical parabola trajectory. So let's discuss them one by one. In the cliff style problem, what happens is an object approaches some kind of cliff or a table or something that's elevated and is projected horizontally. So it's rolling off the table, it doesn't just fall down. As we've seen, you can project something and the objects will land at the same time because of something known as the independence of perpendicular vectors. All right, so what that means is that the horizontal piece and the vertical piece are kind of independent of each other and they're only strung together by one thing, which we'll see later, time. So the object here is moving in a horizontal direction. It's supported by a surface, so it's not falling until it reaches the cliff where it no longer has any support. When it reaches the cliff, it continues its horizontal motion, but also is falling at the same time. And so you get this characteristic half parabola or hafabola pattern over here. Okay, and at some point you'll have a Vx and a Vy and the combined velocity. And what we're gonna see is that this trig stuff that we've been using before comes in handy when we're dealing with how much of the velocity is actually horizontal and how much is vertical. This angle here, because it's falling straight off the cliff, is 0 degrees. The cosine, by the way, of 0 degrees is 1. The sine of 0 degrees is 0. What this means here is that all of the motion is horizontal, and 0 of it here at 0 degrees is vertical. This is all horizontal motion, which is the x direction, okay? And so that's what happens here. Vy naught is simply 0 meters per second at the very beginning before it falls. The next situation we're gonna look at is when we launch at an angle, we have this symmetry, symmetrical philabola, which is a parabola that begins at the same height as it ends. So it goes like this. Okay, so a lot of objects would do this. For example, if a football is thrown, a baseball is hit, it's basically a symmetrical parabola. It may hit the ground just below, but it's pretty close to symmetrical parabola. Soccer ball probably is the closest thing. You're gonna kick it from the ground. It could hit and end up on the ground, and so we may get that effect as well. Here, we've got V naught and its components Vx naught and Vy naught. If we were to calculate that, we'd be using our trigonometry. Vx naught is V naught times the cosine of the angle. Vy naught is V naught times the sine of the angle, theta. And that becomes this. The Vx naught is the adjacent side. We always take the angle with respect to the horizontal. I'll stress that much more later on. Vy naught is the vertical. Relative to this angle, it's the opposite side, okay? So that's this situation where we begin at a particular spot on the ground and at the same height, and it has something called the range, how far to go away. When you launch at an angle and have a non-symmetrical parabola trajectory, that case can be studied too, and we shall. So let's say you have a platform or a cliff and you launch something at an angle theta. Here's Vx naught, here's Vy naught. The object is launched and it continues though past this horizontal reference, okay? So the vertical displacement actually at the very end is less than we began. This is a negative displacement here compared to what we started in the vertical direction. So we'll be able to analyze that as well, see what happens when we have a non-symmetrical situation. All right, very good. So what we're gonna look at next are some of the variables and organizing and managing them that have to do with projectile motion. Greetings peeps. Oh, hello. This is me. She's gonna help us check out the managing motion variables. As you can see, he's been buzzing around this room like crazy. It can kind of keep him still. Well, what up, kid? All right, you go down now. Managing motion variables. So the way to organize this, I think, this may help you actually dissect these problems, is when we divide them into horizontal, vertical, and also a shared or combined piece, because they share some assets as well. So here we go. Let's look at the shared or combined first. It's in the middle. Each of them share an angle, okay? So if the vertical and horizontal pieces are gonna be projected, they may be linked at the very beginning by an angle, and they share a V naught, but that angle is gonna tell us how much of that velocity, the original velocity, is going to be horizontal, Vx. How much is going to be vertical, Vy. And V is the velocity at any moment. It could be at the end of the travel. It could be any moment during the projection and traveling through the air. Then we've got T, and I put 2 down here. T peak is just a special place because we know that when the object is at its peak, there's something special that happens as well on the vertical side. And that is simply this, that the Vy peak is 0 meters per second. Okay, so that's why I put T peak down here, because sometimes it leads us to a variable that has a value, a clue, and there we go. And then there's T, which is always shared between the horizontal and vertical, okay? Time links them together in space. Time links the horizontal and vertical motions together in space. So on the horizontal side, we have X. So that's the X position. And we have Vx naught, which interestingly, for the horizontal side is equal to Vx. These are identical. That equals the original velocity in the horizontal direction. V naught times the cosine of the angle. Here's why. There is no horizontal gravity. There is not. So we're not dealing with air resistance, so there's nothing, no drag, nothing to slow it down. Therefore, Ax is 0 meters per second squared, okay? So whenever you find Vx naught, that's the same thing as Vx in a projectile problem. It's just going to coast through the air. It's going to cruise at that velocity the whole time. The issue is when will it land or whatnot. So it's the vertical side that determines for the amount of time that it's in the air, and the horizontal side is happily cruising along at its original velocity. So on the vertical side, we have y, and we could look at it as delta y if we want to talk about the displacement, but here's the position, y equals something. And Vy naught is V naught times the sine of the angle. As we looked at before, here's the right triangle trigonometry. Vx naught, the adjacent side. Vy naught, the opposite side relative to this angle here, which is bounded by the velocity vector in the horizontal. So there we go. So we have V naught times the sine of the angle is Vy naught. Vy peak we discussed is 0 meters per second. So what that means is that at the very tip of that parabola, the horizontal velocity is still the same, but the object is going to slow down because of the acceleration of gravity in this downward direction. So if an object is moving up, it slows down until it gets to 0. That's the peak of the parabola right there. Vy peak is 0 meters per second. There's no vertical velocity at that very moment. Ay is g. It's the acceleration due to gravity. Okay, this is a known also for all these problems because we're going to study them on Earth. Yeah, we may change this if we study something on the moon. If we wanted to launch something on the moon, what it would be like. But for the most part, we're going to deal with earthly situations here. And so we have the 9.8 meters per second squared, g, the acceleration due to gravity. That would be negative if the y is considered to be positive in the up direction here. If up is considered to be positive, then this would have a negative value over here. And so there we go. These are the variables that we'll have to track. And there's a lot more now because of the combining of the horizontal and the vertical piece. So no longer are we just dealing with a free fall or a launch of an arrow up down or a car that slows down. We now combine these together, and it's going to be really, really important for you guys to keep organized. And so this is one way to do it, to do this on your paper when you try to solve any of these problems. Get these down and they'll lead you to another. For example, if you wanted to find x, the range, you may have information about the vertical side, like the height. You then always, always, always need to find time and then have time help you find the value you're looking for. In this case, maybe the range or the position from the origin. So in one of our next videos another time, I'll actually go through the process of solving a few of the cases that I had shown you before, 1, 2, and 3. But for now, I just wanted to introduce you to the types of problems and the variables that are going to be in play. All right, and with that, it's Morad and Ramesh out.